Large language models, or LLMs, have made incredible strides in understanding and generating human-like text, allowing them to handle a wide range of tasks from answering questions to writing stories. However, as researchers from the Harbin Institute of Technology and the Beijing Academy of Artificial Intelligence point out in their paper, these models often pick up on biases present in the datasets they're trained on. This can lead to poor performance when the models encounter new situations that don't align with those biases. The paper, titled Information Gain Guided Causal Intervention for Autonomous Debiasing Large Language Models, is authored by Zhouhao Sun, Xiao Ding, Li Du, Yunpeng Xu, Yixuan Ma, Yang Zhao, Bing Chen, and Ting Lu. They highlight that during the supervised fine-tuning process, LLMs learn not just useful patterns but also shortcuts based on dataset biases, such as negation bias or popularity bias. For example, in a dataset about basketball players, if most questions are answered with well-known figures like James or Curry, the model might start associating popularity with correctness, ignoring other relevant factors. This makes the model less generalizable, meaning it struggles on tasks where less popular options are the right answers. To illustrate, consider the examples from the paper. In an original dataset, questions like, "Who is the author's favorite basketball player?" are paired with contexts that always mention popular players, such as James or Curry, leading the model to rely on popularity as a cue. But in real-world scenarios, the correct answer might be someone less known, like Morgan Moses, and the model fails because it hasn't learned to look beyond the bias. The authors argue that traditional Debiasing methods have limitations. Many require prior knowledge of the specific biases, which isn't practical because biases vary across datasets and tasks, and new ones keep emerging. Plus, automatic methods based on in-context learning haven't been effective enough due to the complexity and diversity of these biases. To tackle this, the researchers propose a new framework called Information Gain Guided Causal Intervention Debiasing, or IGCIDB. This approach combines ideas from causal inference and information theory to autonomously debiase datasets without needing to know the biases in advance. At its core, IGCIDB works by first analyzing the dataset to identify imbalances that could lead to biased learning. It uses a concept called information gain, which measures how much knowing one piece of information reduces uncertainty about another. In this context, information gain helps quantify how much a particular feature, like the popularity of a basketball player, influences the model's predictions. By calculating this, the framework can pinpoint biased features that the model might be over-relying on. Once these features are identified, the framework applies causal intervention. Causal intervention is a technique from causal graphs, where you deliberately alter parts of the data to break the link between the bias and the outcome. For instance, in the basketball example, if the original dataset only has popular players as answers, the intervention would introduce examples with less popular players to balance things out. This ensures that the dataset no longer favors one type of answer over another. Specifically, the process involves two main steps. First, it automatically generates intervened examples. Using the information gain as a guide, it selects samples where the biased feature is prominent and modifies them to create a more balanced distribution. In the paper's figure, this means changing an example so that a less-known player like Morgan Moses becomes the answer, countering the popularity bias. The goal is to achieve a balanced ratio, such as 1-to-1 between popular and unpopular options. After debiasing the dataset, the second step is straightforward. Perform standard supervised fine-tuning on the newly balanced dataset. This trains the LLM on data that's less likely to reinforce biases, helping it learn more robust patterns that generalize better to unseen tasks. The researchers conducted experiments to test IGCIDB's effectiveness. They applied it to various LLMs and datasets with known biases, measuring improvements in generalizability. The results showed that models trained with IGCIDB performed significantly better on debiased evaluation sets, where biases were neutralized. For example, in tasks involving questions with less popular answers, the debiased models maintained high accuracy without dropping off as much as non-debiased ones. This demonstrates that by intervening causally and guiding with information gain, the framework successfully reduces the model's reliance on spurious correlations. Overall, This method is innovative because it's autonomous. It doesn't require human experts to manually identify biases. It leverages causal mechanisms to understand and alter data distributions, making it scalable for large-scale datasets. By integrating information theory, it ensures that interventions are targeted and efficient, only adjusting what's necessary to achieve balance. In practical terms, this could mean more reliable LLMs for real-world applications, like chatbots or recommendation systems, where biases could lead to unfair or inaccurate outcomes. The paper's approach opens up possibilities for future work, such as applying similar techniques to other types of biases or even multimodal data. To wrap up the explanation of the key contributions, IGCIDB represents a step forward in making LLMs more robust and trustworthy by addressing biases at the dataset level through automated, principled methods.